Hi, I'm Anil Ananthaswamy. I'm a science journalist and author, and currently the science communicator in residence at the Simons Institute for the Theory of Computing at UC Berkeley. It's my pleasure to welcome Professor Andrew Gordon Wilson. Andrew is a professor at New York University's Courant Institute of Mathematical Sciences and Center for Data Science. His research interests include, among other things, understanding deep learning models, including LLMs and vision models, generalization, and reasoning. So, welcome, Andrew.
Thanks. It's really great to be here.
So, today we'll talk of Andrew's work on the connections between transformers, Kolmogorov complexity, universal learning, and the no free lunch theorem. So, Andrew, could you give us a sort of bird's eye view of the no free lunch theorem and its implications?
Yeah, so there are several no free lunch theorems. The most famous is by David Wolpert and McReady, and it essentially says that every learner is equally good in expectation over all data sets sampled uniformly from a distribution over data sets. There are others, for example, there's one from Shayla Schwartz and Ben David, which basically says that no single learner can achieve high accuracy on every problem. And historically, these theorems have often been used to argue that we can't have one method that's going to be good at all sorts of problems because they imply that if it's working really well on one problem, it has to be working poorly on others for everything to average out.
So, this has implications for, like you said, building models that are universal learners, or even when we talk of artificial general intelligence, a model that can be called to be AGI. Have you come across those kinds of objections?
Absolutely. So ever since I started in the field, I've been really interested in automation. I think that's actually a defining feature of machine learning as a discipline. Statistics and machine learning, I think, are quite related and they're often compared to each other. And sometimes I hear ML is really just a subset of statistics or a rebranding of statistics in some sense. But I think they are really fundamentally different disciplines, as different as, say, physics and chemistry. I think they share some of the same tools, but they really have different ambitions. Statistics, in my view, is aiming to equip other statisticians with tools to analyze data, whereas machine learning is trying to automate learning and decision making. People in machine learning want to build autonomous intelligent systems that can operate effectively without human intervention. So they want to remove the human from the loop. And while some of the tools it uses in order to try to achieve this ambition are grounded in statistics, I think this ambition itself is quite different from what statisticians are trying to achieve. And that can explain a lot of the differences in the field. And so, in some sense, I think machine learning is really oriented around automation, but there's a question about to what extent automation might be possible in light of results like the no free lunch theorems. In some sense, machine learning is really aligned with trying to develop systems that will be good at many different tasks at once. And so this is something I've been trying to do since I started in machine learning research at the beginning of my PhD, starting about 2009. And initially, there were a lot of objections. Nowadays, there are fewer objections, I think partly because we're actually seeing systems that are starting to realize this ambition of being simultaneously useful on many different problems.
So I do want to come back to this thing that you mentioned at the end, that we're beginning to see systems that are simultaneously good at many different things. But going back to the no free lunch theorem, you've been looking at why the no free lunch theorem might not be as applicable to real world data sets or the kind of problems that we're trying to solve with machine learning. So could you speak to that a little bit? And then we'll come back to the current state of models like transformers.
Absolutely. So there's this question of how it might be possible to have systems that are effective in a wide variety of different settings and even on completely different modalities of data, say text, images, time series, etc., in light of results like the no free lunch theorems, which have historically been used to argue against something called meta learning, for example, like learning to learn and really, automatic machine learning in a variety of different capacities. And a big part of the answer is that the real world is a small corner of all possible data sets. So the problems that we're modeling are not uniformly sampled from a distribution over all data sets. And in fact, most of those data sets would be essentially noise. They wouldn't really have very much structure. And so we wouldn't be interested in modeling most of those problems. By design, the problems that we're choosing to model do have a fair amount of structure. And perhaps surprisingly, that structure is shared to a relatively large extent. And how that structure is shared, I think, is really an interesting question as well. And yeah, possibly we could talk about that more.
So what do you mean? How that structure is shared? What are you referring to?
Right. So there are some theories, for example, that suggest that the problems we're modeling are some projection of some unified underlying reality. For example, you could describe an image with words or with pixels. And so if you train, a language model or a vision model on data represented in those different ways, in some sense, it might discover similar solutions to whatever predictive task you're considering. That's not really my view. My view instead is that different problems are actually fairly distinct in many cases in terms of like the low-level features that describe those problems. For instance, you could have one problem where you have some sort of salient invariance, like rotational symmetry. If you're modeling molecules, you'll have rotation invariance. Whereas you might have other problems with, say, translation invariance. If you're doing digit classification, it doesn't really matter if you horizontally translate a 2 on the screen, it's still a 2. And so these are very different low-level features that are describing the problem, but they both describe compressions of the problem. And so in some sense, we can view models in machine learning as providing a compression of the data. Once you've trained the model on the data, you don't need the data anymore. The model is the representation of that data. And if the model is able to represent that data with a very small number of bits, then it's able to really compress that data effectively. And in order to do that compression, you need to discover regularities like, say, rotational or translational symmetry or whatever it might be. And those regularities will often help you make good predictions on held out data. And so my view is that what is in common between these different problems that we're choosing to model is compressibility. It's not necessarily like the details of the low-level structure.
So the more compressible the data, the easier it would be to model. And there's something about the different modalities of data that they share, which has to do with this compressibility.
Exactly. So many different problems are compressible, and there are principles, I believe, that will enable certain types of models to find a good compression of all of these different problems at once. And this helps explain the confluence of more specialized models to more general purpose learners over time.
And you formalize this idea by looking at something called Kolmogorov complexity of these data sets. Could you speak to that a little bit and tell us a little bit about what one means by Kolmogorov complexity?
Mhm. So far I've been talking about compression. Kolmogorov complexity is a way of measuring compression for a fixed programming language. The Kolmogorov complexity of data is the length of the shortest program in bits that outputs that data. Um, Kolmogorov complexity, I think, is useful for thinking about compression and generalization in machine learning. It can be upper bounded in order to provide rigorous generalization bounds on the performance of our models. And this is something we did in a paper called The No Free Lunch Theorem, Kolmogorov Complexity, and the Role of Inductive Biases in Machine Learning. And we can basically upper bound this quantity by measuring the compressed file size of the models that we're learning. And what we showed in that paper is that you could have models that would be trained on some particular modality that actually provably will provide good generalization on completely different problems and even different modalities of data. And to give an example of that, we showed, for instance, that a convolutional neural network, which was clearly designed for image recognition, actually had inductive biases, had sort of assumptions that would enable it to make reasonable predictions on, say, tabular data, which doesn't really have structure that's very specifically associated with images. And this is precisely because of this bias for low Kolmogorov complexity. So perhaps a short way of saying this is the distribution of real world data sets tends to be biased towards low Kolmogorov complexity. And so are some of these models that we're using that tend to have good performance on a wide array of different problems.
Well, that brings us nicely to talking about the more generalized models that we are seeing today. But the history of deep learning and deep neural networks has began quite differently. People were building very specific kinds of models, right? You've mentioned convolutional neural networks, but prior to the current wave of stuff that has been happening with transformers, we were building lots of bespoke models. So talk us through a little bit about what came before transformers, and then we can talk about what has happened since.
Mhm. So when I started becoming interested in machine learning in the mid 2000s, neural nets and deep learning were very much out of favor for some of the reasons I gave all these decisions to make and not a great framework to make those decisions. Other ideas were very much in vogue. I was working in an area called Bayesian nonparametrics, and something actually quite interesting about many models that could be called Bayesian nonparametric models is that they have an infinite number of parameters. They're actually more flexible than any possible neural network that you could fit in memory. And this actually has given me a clarifying perspective, I think, in understanding how neural nets work. So there are many phenomena in deep learning, like the ability to fit images with random labels perfectly, but still generalize well when you have structured problems that seem to be in the face of conventional learning theory results related to VC dimension, Rademacher complexity, etc. Overparameterization, having models with more parameters than data points that are still providing good generalization. This phenomenon called double descent, where as you continue to increase the flexibility of the model, first your generalization error decreases as you capture more structure in the data, and then it starts to increase as you start to seemingly overfit the data, maybe pay too much attention to details of the training data that are not going to be helpful for making predictions. And then you decrease error again as you continue to increase the flexibility of your model class. All of these phenomena are actually quite understandable, I think, from this perspective of what I call Bayesian nonparametric modeling, really embracing flexibility combined with a simplicity bias. And so that's actually what a lot of other model classes do, and I believe that's what transformers are doing. But before we got to transformers, in the world of deep learning, it was very common in natural language processing tasks and image recognition problems, etc., to first have the human practitioner essentially encode a lot of domain knowledge into an algorithm. And this knowledge wasn't being learned, it was just being kind of baked into the procedure. And then afterwards, you would do a little bit of learning on top of that. And in the paper I mentioned, we go through all sorts of procedures that can be described in that way. After a while, it became more common to build neural networks that were specialized to certain classes of problems. So you would have convolutional neural nets for image recognition, multilayer perceptrons for tabular data and regression, um, recurrent neural nets for sequence modeling problems, etc. And nowadays, this is all getting subsumed by transformers. So there's been this very clear movement from more specialized models that are hard coding all sorts of knowledge. This is sometimes called feature engineering, towards models which are trying to, in some sense, learn those features that used to be hard coded, but are still specialized to certain modalities of data and specific types of problems, to models like transformers, which are really being used almost everywhere. And so this has been, I think, really exciting and surprising to a lot of learning theorists. And it's an opportunity to really understand something new. It shows us that at least some notion of universal learning is possible. Universal learning meaning that we can make good predictions on a wide variety of different problems that we're trying to model, even problems that seem relatively unrelated. Um, and in some sense, I think that we had evidence that this ought to be possible with some of the model classes we were using before that really did combine flexibility with a simplicity bias. And I think those are really the key ingredients towards universal learning. And we've been studying how transformers can encapsulate those properties.
So, what is it about transformers in particular that makes them better universal learners than what came before? Maybe we can now kind of tie the various things that we've been talking about, the no free lunch theorem, uh, Kolmogorov complexity, the various types of data sets, and the transformer architecture. So this your work kind of brings all these things together.
Yes. So I think there are really two properties we want in a model that's going to be good on a wide range of problems. We want the model to have a large hypothesis space, meaning it can represent many different solutions to a particular problem. And we also want it to be biased towards a simple solution that will be consistent with our data. And so that's some notion of Occam's razor, and that can be formalized in terms of Kolmogorov complexity. Transformers do have a large hypothesis space. So they're very large models. We can look at things like the universal approximation theorems, etc., to argue that these models will be very flexible. And I think what hasn't been known, perhaps until recently, is that these models also do have a strong simplicity bias. And so that's something I've been studying. And I think at this point is somewhat overlooked. I think that we have, as a community, have focused a lot on things like universal approximation. But we haven't necessarily focused enough on what I've been calling inductive biases, which is basically just a fancy phrase for assumptions that will enable learning by example. And that's really what machine learning is. Like you see some data and you have to learn something by example and generalize to new unseen problems. And in order to do that, we need to make assumptions. But what's been interesting and perhaps surprising is that those assumptions can actually be relatively general. And at a high level, one assumption is that we want to use a compressed representation of our problem if possible. And so before talking about transformers, it might be helpful to start with just a simple example that I think a lot of people can understand without very much background. So polynomials, if they're large enough, are very flexible model classes. But if you just have a really large polynomial, like a 10 trillionth order polynomial or something like that, and try using it without any special intervention to fit various different problems, what you'll most often find is that you end up overfitting the data, meaning that you're able to run through the points that you observe perfectly. Like, for example, your function is able to produce the correct labels where you have labels. But then when the model has to make predictions, when the big polynomial has to make predictions, those predictions won't be very accurate. And that's because this model has an expressive hypothesis space, but it doesn't really have this Occam's razor bias. So we can try to instill this bias in a model like this by saying, well, let's actually penalize the higher order coefficients of this polynomial more than the lower order coefficients. And so our penalty can be order dependent in some sense. And so what that means is if we're doing regression and we say data points, for example, that look almost like they're on a straight line, then even though this trillionth order polynomial can run through those data points in all sorts of different ways, they can have a very, very wiggly looking function, they'll prefer to fit it with a straight line because there's a penalty incurred by using those higher order coefficients. But then if it starts to see data with more and more sophisticated structure, it does have the capacity to fit that data. But in doing that, it will still tend to prefer a simple explanation over a more complicated one. So maybe by necessity, the explanation becomes a little bit more complicated, but it will still have the bias towards the simplest explanation that's consistent with what we observe. And so that's an embodiment of Occam's razor, and that's something that we can control by doing this type of regularization, by saying, okay, we'll just use the low order terms if you can, and gradually increase, the order of your model as necessary, essentially. So this is a model that actually can provide, demonstrate benign overfitting, this phenomenon I mentioned where you can fit noisy labels perfectly and still generalize unstructured data, and it's not a neural network. And so that phenomenon was originally presented in a paper called Understanding Deep Learning Requires Rethinking Generalization, which implies that this is something that's specific to deep learning And we need to, profoundly rethink generalization in order to understand it. And I think actually neither are really true. We've just shown that we can reproduce this kind of behavior with a model as simple as a polynomial, and that's about as simple as it gets. And it's fairly readily understandable. And it's not even that we don't have theoretical frameworks that can explain this already either. So there are, for example, Pack-Bayes frameworks, finite hypothesis bounds, which we present in this paper on no free lunch theorems, that don't focus entirely on the size of the hypothesis space, but also consider what types of solutions are going to be a priori preferred by the model. And so with a Pack-Bayes bound, you can actually have an arbitrarily flexible model that will provably generalize. And so this generalization theory existed long before this paper. So this goes back several decades. And with transformers, what we've been finding is that they also have this simplicity bias. It's more implicit. It's not a consequence of specific regularization, as in the polynomial example I gave. It tends to be related to the size of the model, which might be a bit counterintuitive. So the larger the transformer, the stronger its compression bias, the more it wants to kind of compress the data. And this is true for a transformer that's been said to be pre-trained on data, but it's also true of a transformer that hasn't even seen any data before. If you just randomly initialize its parameters and have it generate sequences, those sequences will have lower Kolmogorov complexity the larger you make the model. And by lower Kolmogorov complexity, I mean, for example, you'll see repetition and other sorts of patterns that make those sequences more compressible.
So transformers have a bias towards simplicity or towards low Kolmogorov complexity, and they combine that with a very large hypothesis space or expressivity, right? So those are the two ingredients you need for a good universal learner.
Yeah, exactly. And I think there's an open question right now about how we can control some of these biases, since it's an implicit bias in a transformer. It's unclear if we can control it more directly or interpretably than just increasing the size of the model. It's a little bit uncertain exactly why increasing the size of the model increases this bias for simplicity. There are some intuitions that I think are interesting, and this could get in the weeds a little bit, but very briefly, um, when we're training these models, we basically have some objective function that we want to minimize. So this is sort of like an error function, like the distance between our observed data points and what the outputs of our model are. And if this objective function has solutions for the parameters of the model such that we can perturb the parameters and still do a pretty good job of reconstructing the data, those solutions are said to be flat. And those flat solutions tend to be more compressible because by definition, we don't need to represent them with as much precision. And if we have a larger model, those flat solutions tend to occupy an exponentially increasing volume in this objective function. And so they're much more discoverable. And so this could be an explanation, for example, for this double descent phenomenon I mentioned. So once you're in this regime where you basically are reconstructing the data perfectly, and you're just increasing the size of the model, you're actually making it easier to find solutions that are more compressible, and that's why they generalize better.
So, Andrew, maybe this brings us to our final question. Looking ahead, given that large language models, today's large language models are have transformers as their main architectural component, and there's all this talk about LLMs as we scale them up could take us towards AGI, artificial general intelligence. Do you think given all that you've said about the power of transformers and their ability to be, better universal learners than anything that came before, do you think that LLMs are going to take us towards AGI?
I don't think they are alone. So despite the seeming convergence of neural network architectures towards transformers across several different modalities, I think this model class is still limited. So transformers, like most standard architectures, are limited by their expenditure of bounded compute per input instance. And this property prevents transformers from implementing many low complexity algorithms that would generalize well, and it limits the probability distributions they can represent through autoregressive generation. And several papers have observed that transformers fail to solve simple problems with, say, recursive structure. Other papers show that transformers solve problems inefficiently and can learn shortcuts with poor generalization in practice. And even with what's been called chain of thought prompting associated with the new release of the GPT 4.0 models, um, we don't have basically sort of a Turing complete representation due to a finite context length with these transformers. And so there are really a lot of open questions. I think we need a lot of architectural innovation. Personally, I've been very excited about how our modeling assumptions surface as some sort of algebraic structure. And so, for instance, you can derive a convolutional neural network by starting with another architecture called a fully connected neural net and removing a lot of the parameters and then enforcing parameter sharing. And this basically means you're replacing a matrix that is called a dense matrix with a matrix that has a lot of parameter sharing and sparsity. And this is an instance of how our modeling assumptions basically translate into some kind of matrix structure. And so I've been really interested in what sorts of matrix structures might be more universal and can lead to better performance as a function of computational budget. And this connects to things like scaling laws that people have observed for transformers. At the same time, I've been very surprised. So we've had a number of papers that have been using transformers that are just pre-trained on text completion to solve other problems. And it's not just that they can make okay predictions, which might be surprising in other settings. Actually, they can be very competitive. So a good example of this is when we took a transformer which had only been trained to predict the next word in, sequences of words, froze the representation entirely, didn't update it at all, and then had it make forecasts on time series prediction problems, like you're trying to predict the price of a stock into the future, for example. And this worked better than purpose-built time series models that had been trained specifically on that time series data. So this was in some sense quite mind-blowing. This is completely in a zero-shot capacity. And so this suggests to me that in a few years, if there's a research effort focused around developing transformers to do particularly well on time series, we could see, whatever comes of that being significantly better than all of the alternatives. Similarly, we've use transformers for material generation, starting from models that have been pre-trained on text to generate, say, stable inorganic crystals. And this has also worked extremely well. And perhaps surprisingly, one of the ingredients that was really important for success in this setting was pre-training on text. And so text and completion and materials generation don't seem to really have very much in common. But what they likely do have in common is that by pre-training on text completion, you learn things like Occam's razor, which will be very useful for, say, time series forecasting, where you have a small amount of the potentially available information typically, and, say, materials generation, where you actually do need to try to discover salient symmetries like rotation invariance, etc. And so on the one hand, I think transformers are limited, and there's a lot of work that's ongoing that is modifying these architectures so that they can solve certain types of problems much better and approach other problems that are completely unapproachable right now with current transformer models. However, they are surprisingly general, I think much more than anyone expected. And it's also been very interesting and surprising that pre-training on text can be useful in so many other different downstream applications.
Well, great. Thank you very much, Andrew. That was very enlightening. Thank you for being on this episode of Polylogues for the Simons Institute. I appreciate your time.
Likewise, my pleasure. It was really great chatting with you.